Today I'm going to do a review on this paper called Electrons on the Brink. Fractal patterns may be key to semiconductor magnetism. Now, I've been sitting on this paper for quite some time, just waiting for the right time to review it and to present it. And so since the fractal paradigm has come up in discussion in my community section, I think this is a good time to review this paper. Now, this paper was published in February of 2010, so that's more than 10 years ago. And so this is not new. This is not new. I've known about this for a long time. And this is actually, to me, this is almost I'm going to say this is one of the most important papers that I ever read in terms of the fractal paradigm and in terms of the principle of incommensurability. Now, as you can see in the title, there are a lot of key words in here that fit the discourse, the conversation that I've been trying to have in my video series. Of course, it's got the word fractal, it's got the word magnetism, it's got the word semiconductor, and of course, without semiconductors, we wouldn't have the computers that we have today, and I probably wouldn't be doing the work that I'm doing if not for semiconductors. And so the understanding semiconductors is super important. The word electrons is in here, and I know the word electron is a trigger word for some people. You know, there are a lot of people out there saying electrons don't exist. Ken Wheeler says electrons don't exist. Nikola Tesla says electrons don't exist, and that's not exactly true. So when I use the word electron, I'm talking about the phenomenon of electron. The phenomenon of electron exists. Okay, so whatever it is that we are calling electron, that mainstream calls electron, that people call electron, is a phenomenon. So whether it's a particle, whether it's a wave, whether it's somewhere in between, is neither here nor there for this discussion. Okay, so don't get triggered by the word electron. Okay, this is a paper is about electrons and how they behave under different circumstances. And so this on the brink is another term for phase transition. Okay, so this is an action-packed title. And the study that this group did, the Princeton group, is really, really interesting. In terms of the fractal paradigm, these are the two questions that we are asking. The scientific question is, what are fractals? And the philosophical question is, why fractals? Okay, why do fractals exist? Under what conditions do fractals come into being? Okay, so in terms of answering this question, what are fractals? This is my long definition of fractals that covers everything that I understand and know about fractals. And so let's just go through this. Fractals are emergent properties, okay, they are outputs of an iterative or recursive feedback system or phase transition. Now, in order to understand the article that I'm reviewing today, this is the key word here, is phase transition. So mathematical fractals are created using iterative or recursive feedback systems. Nature also uses recursive or some sort of feedback system, is often, if not always, involved in the creation of fractals. And very importantly, it is also seen, fractals are also seen in phase transitions. Okay, so fractals are emergent property of iterative or recursive feedback loops or phase transitions that form patterns that manifest as complex coherent structures. Okay, so coherent is a key word here. So these complex coherent structures have the property of self-similarity and scale invariance. And of course, when you look at the Mandelbrot set, when you zoom into it, you find many other sort of mini many Mandelbrots that are similar but at different scales. And so scale invariance is an important feature of fractal geometry, and self-similarity and scale invariance. So fractals are emergent properties of an iterative feedback system or phase transition that form complex coherent patterns with the property of self-similarity and scale invariance with specific boundary conditions and or complex morphologies. So in terms of the Mandelbrot set, the boundary condition is this boundary right here. Okay, this boundary right here. And the complex morphology is also on this boundary right here. Okay, so this boundary I call it a separator. It separates, let's call it inner world from outer world. It is a separator by definition. It is a boundary condition. And I also refer to this as an event horizon. So these complex morphologies that are generated by some iterative feedback system or phase transition have a fractal dimension which is greater than the topological dimension. And what I mean by that is, so in terms of the Mandelbrot set, the boundary that separates inner world from outer world is technically a one-dimensional, freakishly complex one-dimensional curve with a fractal dimension of 2. So the fractal dimension in any fractal always exceeds the topological dimension. So the fractal dimension uniquely quantifies the level of complexity of the fractal pattern. So the higher the fractal dimension of a fractal curve, of a fractal pattern, uniquely quantifies the level of complexity. So if you have a higher number, higher fractal dimension, you have more complexity. And so the fractal dimension of the Mandelbrot curve, the freakishly complex one-dimensional curve that separates inner world and outer world with a fractal dimension of 2, is basically saying that this is the most complex that this one-dimensional curve can be. It is maximally complex. Okay, so this is a maximally complex so I remember reading a quote, and I can't remember where it was from, but basically they said if the Mandelbrot set curve, if the Mandelbrot set, this one-dimensional curve, was able to curve into itself even one quantum more than it already is, it would pop into the third dimension. And so the fractal dimension uniquely quantifies the level of complexity of the fractal pattern. So the full definition, I'm going to read it in full. Fractals are emergent properties of an iterative or recursive feedback system or phase transition that forms patterns that manifest as complex coherent structures with the property of self-similarity and scale invariance, with specific boundary conditions and or complex morphologies that have a fractal dimension greater than the topological dimension that uniquely quantifies the level of complexity of the fractal pattern. Okay, so that is my definition of what are fractals, and it also gives a little idea of where fractals come from, i.e. from iterative recursive feedback systems or phase transitions. So in terms of the mathematical fractals that we know and love, i.e. the Mandelbrot set, the Mandelbrot fractal, it can be generated, it is generated using very, very, very simple, mathematically simple rules. Okay, so to generate the Mandelbrot set, all you need is the concept of two-dimensional numbers, right? Complex numbers as two-dimensional numbers. And the equation z equals z squared plus c. Okay, so this is as simple as math gets. You can't get mathematically more simple than this, and yet this mathematical fractal, this mathematical formula, generates the most complicated one-dimensional fractal curve that could possibly exist. And so this is, maximally fractal. This is as fractal as you can get. It is as complex as you can get. This very simple mathematical formula is able to do this complex thing. So that is the beauty of fractals in nature. I mean, nature doesn't try to make fractals. You plant a seed and the plant grows and it's a fractal pattern, and nature is not trying to make a fractal pattern. This is just what nature does. And so nature is freakishly simple, as Ken Wheeler says, as I believe is true. And the fractal patterns are emergent properties of some very simple feedback processes in nature that generate the beautiful fractals that we see in nature. So with that out of the way, I'm going to proceed with the review of this paper, Electrons on the Brink. Fractal patterns may be key to semiconductor magnetism. Just as the heartbeats of today's electronic devices depend on the ability to switch the flow of electricity in semiconductors on and off with lightning speed, the viability of the spintronic devices of the future, technologies that manipulate both the flow and magnetic spin of electrons, will require similarly precise control over semiconductor magnetism. Achievement of this goal necessitates a detailed understanding of what happens at the exact transition point when a semiconductor changes from a metal to an insulator, a phenomenon shrouded in mystery despite decades of examination. Okay, so the phase transition between from a metal to an insulator has been shrouded in mystery. Nobody really understands it, or at least at the time before 2010. Okay. But in results published February 5th, 2010 in the journal Science, a Princeton-led team of scientists has observed electrons in a semiconductor on the brink of metal insulator transition for the first time. So caught in the act, the electrons formed complex patterns resembling those seen in turbulent fluids, confirming some long-held predictions and providing new insights into how semiconductors can be turned into magnets. The work also led to the production of smaller and more energy this work could also lead to the production of smaller and more energy efficient computers. So this is a quote from the paper. The spatial structure of the electron waves inside a given material determines how well it conducts electricity. Okay, if the waves extend throughout the metal, we get metallic behavior. But if they get localized or stuck in specific regions, electricity stops flowing. The way in which electrons undergo this transition in certain semiconductors also appears to play a big role in how they become magnetic. In their natural state, semiconductors such as silicon or gallium arsenide are insulators, that do not conduct electricity. Now, insulators, what are insulators? What do you think of when you think of insulators? You think of dielectric. In fact, the dielectric constants of silicon and gallium arsenide are, 11. So silicon, I think, is 11.9, and gallium arsenide has a dielectric constant of 10.4, something like that. They have a high dielectric constant. Okay, so for decades, scientists have known that they can transform these insulators into metals which conduct electricity by replacing some of the atoms in the chemical lattice structure with other atoms. For instance, replacing the gallium in the gallium arsenide with zinc or manganese. This process is called doping, changes the number of electrons in the material to enable the flow of electricity, but also introduces disorder into the lattice structure that can hinder the electrons' movement and or cause them to become stuck or localized. The conduction is able to occur only if the electrons can hop from atom to atom in the structure, slaloming among the randomness and disorder where the lattice has been perturbed. And so that's why it's a semiconductor and not a full conductor. The idea of electron localization goes back to the seminal work of Philip Anderson, who won the Nobel Prize in 1979 in part for proposing that localization can occur for quantum particles, including electrons, when they encounter random obstacles such as in doped semiconductors. While research over the decades has found evidence for Anderson localization in many materials, the electron waves undergoing this transition never before have been visualized directly. At the transition point, computer simulations have long predicted the emergence of complex, non-uniform patterns of electron waves, like the flow of water in a rocky river. So their simulations predict turbulence. Yazandi's team originally set out to understand how doping a gallium arsenide semiconductor with manganese atoms would convert it to a magnet and turn on electrical conductivity in the compound. After team members at the University of California, Santa Barbara added manganese atoms to the lattice structure, the researchers used specifically designed scanning tunneling microscopes at Princeton to visualize the electron states in the material. Finding themselves confronted with complex spatial patterns of electron waves, the scientists realized that the patterns they saw were in fact those predicted for electrons on the brink of localization. In these patterns, the majority of the electrons are distributed across the surface of the semiconductor in a series of interconnected puddles that resemble fractals, self-similar shapes that repeat themselves on increasingly smaller length scales. Self-similarity, scale invariance. Self-similarity, scale invariance. Fractals commonly are associated with objects in nature, such as coastlines or snowflakes, but they have never before been seen for quantum particles. So this was the first time they're seeing fractals at the quantum level. These observed patterns have important implications for how a semiconductor becomes a magnet. All electrons have a property called spin, which describes the way they rotate on their axes, generating a magnetic field as they do so. If the spins of the neighboring electrons in a given material are opposite one another, these magnetic fields cancel each other out. But when the spins of neighboring electrons in a material are aligned, such that the electrons are rotating in tandem like synchronized swimmers in a pool, the material itself becomes magnetic. This alignment only occurs among electrons of certain elements, including iron and manganese. Okay. While it was assumed that magnetism in manganese-doped gallium arsenide occurs because the spins of all the manganese electrons in the doped semiconductor become aligned uniformly, the team's results suggest that this is not the case. Okay, so some scientific assumptions turn out to be not true. In other words, they were wrong. The alignment of the spins depend on location of the electrons within the fractal puddles, indicating that there are likely areas of strong and weak magnetic interaction in the material. And so their original assumption was that all the manganese in the semiconductor contributed to the magnetism, and now they're finding that they were wrong, and that there might be areas of strong and weak magnetic interaction in the material, where the strong interactions are in the fractal puddles. So here's a quote from the paper. We have shown that electrons move and live in these jagged puzzles, so it is only natural to consider that manganese atoms that reside within each puddle are interacting with each other and giving rise to magnetism, Yazandi said. In this view, where the puddles are not, we have manganese atoms, but they are not interacting or contributing to the magnetism. The puddles become part of the story to understand how magnetism comes about. So now they need to study these puddles to try to understand how magnetism comes about when you dope these materials. Okay. Manganese-doped gallium arsenide has been at the heart of many recent technological advances, and a precise understanding of what causes magnetism in these semiconductors and how to control it will be necessary for the realization of one of the most promising applications of the material, computer chips able to both process and store information. In current devices, chips made of semiconductors such as silicon are used to process information, which is then stored in hard drives made out of magnetic materials such as iron. If the magnetism of a material could be switched on and off, the same chip could be used for both purposes, paving the way for smaller and more efficient computers. So this is really interesting. This is really interesting that, that smaller computers could result from fractal puddles of electrons. In the future, the team intends to explore the connection between optimizing magnetism and the shape of the fractal puddles to find further clues for the mechanism of magnetism and develop ways to enhance it. Their techniques will also allow them to explore whether electrons form similar patterns at the brink of other phase transitions, such as from conductivity to superconductivity. So in this paper, they also have a link to a video, and in this video, they actually show the transition from metal to insulator. And so here is what they say about the video. So this video depicts electron wave functions measured in a manganese-doped gallium arsenide semiconductor based on their energy, illustrating an example of extended and localized electron states and the transition between them. The colors red, orange, and yellow indicate areas on the surface of the semiconductor where electrons are most likely to be found at a given point in time, while the blue and green indicate areas where electrons are unlikely to be found. At the beginning of this video, the electrons are extended across the surface of the semiconductor as in a metal. So at the beginning of the video here in this image here, the electrons are spread out over the material and the material is behaving like a metal. Okay, so at the brink of transition, which occurs when the energy level in the upper right hand corner is 0, the electrons are distributed in an intricately shaped fractal puddles. Okay. After crossing this divide, the semiconductor becomes increasingly insulator-like, and the electrons are clumped together in small regions, having been trapped or localized by the disorder in the material. In other words, when the electrons are behaving more spatially, the material behaves more like a metal. And when the electrons are behaving more counterspatially, when they clump together, they behave more like an insulator. And there is a sweet spot, a phase transition from the metal state to the insulator state, which has the property of self-similarity, where the patterns have a property of self-similarity, where the material behaves like a semiconductor, where it is partly conducting and partly insulating, and you see the property of self-similarity in the patterns generated by the electron waves, or whatever it is they're measuring in their experiment. So what this tells me in terms of the principle of incommensurability is that insulators and metals are incommensurate principles. Insulators and metals are incommensurate principles. Okay, so when the electrons are behaving more spatially, they behave like the material behaves like a metal, and when the material, when the electrons are behaving more counterspatially, when they're clumped together into discrete clumps or regions, the material behaves more like an insulator. And so we have now just defined two more incommensurate principles. Insulators and metals are incommensurate principles. Insulators are not metals, and metals are not insulators. But insulators and metals can work together to create a semiconductor, for example. And so that was the purpose of this video, was to review this paper, very interesting paper, and to identify two more incommensurate principles, insulator and metal, and to also show you how, basically show you how phase transitions can also be responsible for generating fractal patterns. Okay, so the principle of incommensurability, as I said, is not just one thing, it is many things. And fractals can occur for various different reasons, and phase transition is another way that fractal patterns can emerge in nature. Okay, and we will, I've seen this over and over and over again in many other situations and many other papers I've read. It seems that phase transitions are a key to understanding the fractal paradigm. And so that is all I'm going to do for today, but I really felt that it was important to get this out right now because of, the debates I've been having with people on the fractal paradigm. Fractals are not just math. Fractals occur in nature. Fractals occur in phase transitions, and phase transitions are not math. Phase transitions are real. There is a real phase transition from the metal state to the insulator state, and in that phase transition, fractal patterns appear naturally. They are an emergent property. Fractals are an emergent property of in this experiment, the fractal pattern is an emergent property of a phase transition. Okay, so very important point to be made here, and so I hope this helps you understand not only the fractal paradigm, but the principle of incommensurability. There's one more thing I want to say. Someone recently commented on my community section. They said, if you can understand the precursor to a fractal, then you will understand fractals better. And so in my mind, the principle of incommensurability is the precursor to fractal geometry. So fractal geometry cannot exist without the principle of incommensurability. Fractal geometry appears at the interface between incommensurate principles always. So that is my opinion. It is my opinion that fractal geometry appears at the interface of incommensurate principles, either physically, as can be seen here in the mathematical fractal of the Mandelbrot set, or in temporal phase transitions. Okay, so the principle of incommensurability, in my opinion, is the precursor to and is a requirement for fractal geometry to emerge in our universe.
They clearly were FBI agents. They were dressed like FBI agents. I can tell the difference between FBI agents and, let's say, drug enforcement agents or